We're going to finish talking about the intensities of spectral lines by talking here about the concept of the population of the states and how that affects that intensity. Okay, so we've already talked about the transition dipole moment. We've already talked about the Beer-Lambert law and how those control the intensities. There's one more topic, which is the population. All right, so think about a molecule that might have a set of energy states like this, 3, maybe 4, and this is what we call the ground state. That is the first excited state, second, third, and so forth. Okay, so we're going to do spectroscopy with this system by shining photons of various wavelengths and see which ones are absorbed. Okay, so when you get an energy for a photon that is resonant with these two energy states, then you might observe that the system goes from this ground state to the first excited state. Okay, but if you actually have molecules here in this first excited state, it's also possible that you can get another photon to absorb that and generate a transition between E1 and E2. Okay, those lines are all possible. Now, what you have to realize though is that when you actually take the spectrum, there's going to be a different intensity of the line that goes from, that bridges the transition between E0 and E1. That intensity is going to be different from the intensity of the line that bridges the transition between E1 and E2, E2 and E3, and so forth. Okay, so the question is, well, how do we determine which is the transition that gives rise to the most intense line? Well, that is actually related to the population of each one of the states. Okay, so obviously, if we're at room temperature, say 300 Kelvin, most of the states are going to be, or most of the molecules are going to be in the ground state. Okay, so you can say that if you have, say, 10 molecules, it's quite possible that maybe 7 of them will be here in the ground state, so 1, 2, 3, 4, 5, 6, 7. Okay, and then maybe you have enough energy for 2 to be in E1, and then for 1 to be in E2, right? So when you take the spectrum of this molecule, the transition that is going to be more intense is the one from E0 to E0, okay, and then you're going to be maybe observing a little bit of E2 to E1, and then very rarely from E2 to E3, and if you don't have any states in E3, then you cannot observe the transition from E3 to E4 and so forth, right? So essentially what this picture, or the picture that emerges from this, is to say that you're usually going to be observing transitions from the ground state to energies above, and very rarely you're going to have a chance to have substantial population in the excited state to be able to observe transitions from here to upper levels. Well, it turns out that there's actually a law that allows us to calculate exactly how many molecules you have in this state versus that, and versus that, or calculate the relative populations of those states, and that is the Maxwell-Boltzmann distribution law, which we actually talked about at the start of last year. So here we have that the ratio of the populations between that state E0 and that state E1, so N1 over N0, is equal to just the exponential of the difference in energy between those two states, 0 to 1, over kVt. Okay, kV, that's Boltzmann constant if you actually have this energy in joules. Okay, so from here, we actually already can compute that type of population ratio. Okay, so in the book you have an illustration in which you're being asked to calculate the following. So suppose that you actually have here the 1s orbital, and then the 2s orbital, the 2p orbitals, and so forth, 3s, and other orbitals. Right, so the book is actually asking you to calculate, or the illustration in the book is asking you to calculate what is the population between the 1s orbital and the 2s orbital. So here you simply have to calculate the difference in energy between the 1s orbital and the 2s orbital and divide over k sub b t. Okay? Now, we actually know what the energy of the orbitals for the hydrogen atom is, right? That is equal to minus a constant, and then effective charge squared over the principal quantum number squared, right? So you have a way to calculate here the energy of the 2s orbital and the energy of the 1s orbital, can take the difference and then calculate the ratio of populations. And what you will see when you punch the numbers is that virtually all of the atoms, all of the hydrogen atoms are going to have the electrons in the 1s orbital. There's going to be essentially 0 atoms that you actually have with electrons in the 2s orbital. What that means is that when you're doing spectroscopy of the hydrogen atom, the transitions that are going to be more intense are those that emerge from the 1s. Okay, so from the 1s you can go to the 2p's, as we have seen using the selection rules. From the 2s you will be able to go to the 3p's, but again we know that because you don't have enough population in that state, that transition is not going to be very intense. Okay, so this kind of finishes the discussion about the intensity and what of the lines in the spectrum and what does it depend on. So we say that it depends on the Beer-Lambert law, concentration through the Beer-Lambert law. It depends on the transition dipole moment concept, and it also has to do with the populations of the states that are involved in the transition.